Hi. Today I start another sort of equation which is called wave equation. So we are solving the equation. We are looking for a function u of x1, x2, and so on, xn t, and the equation is d2u dt square equals c square Laplacian of u in derivative x, or d2u dt square equal c square d2u dx1 square plus and so on plus d2u dxn square. So u is a function of x and t. X is vector x1, x2, xn. No, this equation, why it is called wave equation, it is not because it does not describe the waves on the surface of water. It is described by more complicated equation. It describes with good accuracy the acoustic waves in the air, for example. In other words, the sound. Yes. So no, I will not enter in further details, physical details. I would like to consider this equation as differential equation and find the ways to solve it. We consider first the simple class of solutions. It is plane waves. It is the wave of the solution of the following form: u of x1 xnt equals u of x1t. So it's a solution which depends only on one coordinate, x1. So say if we have solution in the plane, we have x1 and x2, then the solution depends only on x1, so it is constant on any line. X1 is constant, it is x1. x1 is constant. If it is in x1, x2, x3, yes, so it is x1, x2, it is x3, then solution is constant on any plane. x1 is constant, orthogonal to the x1 axis. So therefore the name plane waves. Now if you substitute this into the equation, you have d2u dt square equal c square d2u dx1 square plus and all other derivatives are zero because u depends only on x1, so it is constant in the direction of x2, x3, and so on. So only this remains. This is the string equation, our old friend string equation. And so we can immediately write the general form of solution. U equals V of x1 minus ct plus w of x1 plus ct. Where v and w are two arbitrary functions, to have a classical solution to arbitrary function of class C2. So we have this solution, and we see that this function v propagates along the x1 axis with speed c, like this, without changing the shape. And w propagates with the same speed in opposite direction. So from here we have the c speed of sound. Yes, nothing more. And here I write c square. No, if I write here c, then some coefficient c, then here would be square root of c. I prefer this form. Now, all the theory does not depend much on this coefficient, so I consider the simplest case c equal 1. So, since this moment, we have the equation Laplace u tt equals Laplacian u with respect to x without this coefficient. Coefficient is 1. In physics, this is achieved by changing the units of measurement. So if we need the simplification, we just change the units. Okay, let us go. So if c equals 1, you have a plane wave. U of xt equals v of x1 minus t plus w of x1 plus t. Yeah. Now we can turn our coordinate system, and instead of x1 we can have different axes. What is important, we can write this equation, this solution in the following form. Let us introduce the vector E1 equals 1, 0, and all other zeros. And then you have u of xt equals v of what is x1. It is E1 dot x, yes, minus t plus w of E1 dot x plus t. Yeah, it is the same. But with this we can generalize it to any direction. So let us take any other unit vector. Yes, let me call this vector A. Yes, A in Rn, length of A equals 1. So I take this vector, and then I can write the function u of xt equals v of A dot x minus t plus w of A dot x plus t, where A is arbitrary vector. No, in fact, it is a vector whose tip lies on the unit sphere of radius 1. No, we can take, in fact, any, say, this term. because if you want to have this, we have take minus a, and that will be w minus a minus t is w a x plus t. So this means that the general plane wave has the form plane wave u of xt equals v of a dot x minus t. It's enough. We can any plane wave represent in this form. Now we can take linear combinations of plane wave moving in different directions. We can have finite or infinite sums of this plane wave. We can have integrals of this plane wave. Here a, let me write here parameter a. A is for any a vector, unit vector a, we have, if you have some plane wave, some function v, then we can integrate this family over parameter a. A runs over the unit sphere. And so we have a lot of solutions of the wave equations, which are derived from solution of string equation, but we may suspect that in some sense all solutions have this form. In some sense it is really true, but it is a longer way to have the results which I am going to explain you. So let me leave it as it is in the same. I leave it at this point because no, it is hard to explain everything. So now we have the simplest class of solutions, plane waves. For now it is enough. And now I would like to go to more interesting for me now class of solutions, which I call spherical wave. Spherical wave. It is the following solution, or it has the following form. U of xt equals v of module x t. Let me write v of r t. R is the distance from the point x to the origin. So at any t, the levels, every sphere is the level surface of this solution, because for any t on the sphere absolute value of x or r is constant. Yes, so solution is constant. So we can imagine that at the origin stays some source of waves, and these waves are propagating from this source in all directions, and what the result will depend only on time and on the distance to the source of these waves. And so my next goal is to study these radial solutions. So uxt is v of rt. U satisfies the equation d to u d t square equals Laplacian of u. Now, if u is such a radial function, at every t depends only on radius r, then we have to express this Laplacian for radial function. In fact, we have already done it when we studied the fundamental solution of Laplace equation. So let me write the result. So result Laplacian u equals v r r, second derivative of v respect to r, v of rt, plus n minus 1 divided by r dv dr. Yes? If v u has this form, what is written here, then Laplacian of u having this form is given by this simple expression. We have already done it, so let me take it as known. And if you substitute it into the equation, you have the following equation. V, this time it is v, v tt, second derivative with respect to t, equals v r r plus n minus 1 divided by r v r, where n is dimension of our space. Now, practically we are interested in n equal 2 and 3. Here we need some trick. The first trick is the following. Let us take n equals 3. Yeah, it is the most useful, and at the same time it turns out the simplest case, n equals 3. And now for n equals 3 you have equation v tt equals v r r plus 2 divided by r v r. And now I wanted to make some substitution. V of rt equals r to some power alpha, which we have to should find. Alpha can be done arbitrarily, times w of rt. Yeah? And now let us substitute it into the equation and find alpha can be done arbitrarily, and for some alpha some terms will cancel, and maybe we can simplify this equation, because without this it would be just the string equation, but this term can be nasty, so we have to somehow kill it. So we'll kill it by this substitution. So v tt equals, no, it does not include r, so it is r to the power alpha w tt. Yes, it is no problem. And about the derivative in r. V r equals alpha minus 1 W plus R alpha WR. V R R equals alpha minus 1 W plus alpha R, I'm sorry, alpha minus 1 R alpha minus 2 W plus alpha R alpha minus 1 W R plus here again alpha R alpha minus 1 WR plus R alpha WRR. Aha, we can, no, let me write it again. It is alpha minus 1 R alpha minus 2 W plus 2 alpha R alpha minus 1 WR plus R alpha WRR. Now let us substitute it into the equation. So we write R to the alpha WTT equals what? VRR, it is alpha minus 1 R alpha minus 2 W plus 2 alpha R alpha minus 1 WR plus R alpha WRR. Now plus 2 divided by R plus 2 VR, it's here, alpha R alpha minus 2 divided by R W plus 2 R alpha minus 1 WR. Okay, and now let us simplify it. So R to the alpha WTT equals, first of all, R to the alpha WRR plus, what about WR? It is here and here. So, this and this. 2 alpha plus 2 R alpha minus 1 WR remains terms with alpha plus alpha minus 1 R alpha minus 2 plus 2 alpha plus 2 alpha R alpha minus 2 W. No, at the first glance, nothing good. But if this and this coefficients are 0, then we are remained with the string equation. So let us check. Let us find alpha. Alpha is in our hand. So that 2 alpha plus 2 equals 0. So we are looking for alpha such that 2 alpha plus 2 equals 0 on one hand, and alpha minus 1 plus 2 alpha equals 0. Now, you know, this is two equations with one unknown alpha. Yes, but in fact there is other unknown, it is dimension. Here I write n equals 3, but this is half of solution, because I should write here arbitrary n, then n will enter here and find alpha and n such that. So I gave this, took this half, because I knew the answer, so just to make the life a little bit easier. So from here is alpha equals minus 1, and here if I substitute alpha equal minus 1, so it is minus 1 times minus 2 is plus 2, plus 2 times minus 1 is minus 2, the sum is 0. So alpha minus 1 is solution both of this and this. So it is a little miracle. So alpha is, so if you take alpha is minus 1, then remains only of this. So if V is R minus 1 W of RT. And then W satisfies the equation R minus 1 W TT equals R minus 1 W RR. Yes? No, this means W TT equals W RR. This is a string equation. String equation. Yes? And so we can write our solution in the form W of RT equals, say, phi of R minus T plus psi of R plus T. Yes? And we divide, after this, V of RT equals 1 over R phi of R minus T plus psi of R plus T. Yes? And V of R T is a solution, so after all U of xt equals 1 over module x phi of module x minus t plus psi of module x plus t. Yeah. So this is solution, general form of this spherical or radial solution, solution where x enters only through module x, the length of x. Yes? So, very good result, but what it is very good, but what it is good for? Yes. So, the next move is that from this result I will extract the formula for solution of general initial value problem for the wave equation in 1 minute. Okay, let's continue. So we have a general form of radial solution of the wave equation in 3-dimensional space. It is important. It is not in any dimension, just in 3-dimension space. So let us continue consider the simplest case of such solution. Substitute here simplest function. As you know, the simplest function is not 0 and not 1 identically. It is delta function. Yeah. So I consider the function, say k of xt equals 1 over module x delta of module x minus t. So, what is it in simple words? In simple words, delta of module x minus t, it is for any point, for positive t positive. Consider the sphere of radius t, so module x equals t, this is the sphere, and delta function is concentrated on this sphere because delta function of one variable, delta of x, is concentrated at 0. So it is concentrated at the point where module x equal t. It is, in fact, how can you find it? Delta function was defined by the following identity: integral delta of x f of x dx equals f of 0 for f is a continuous function. Yes? So delta function on the line is concentrated here. So if you multiply, if you take integral of this of delta function, it is 1. If you multiply it by constant, it is this constant. But if you multiply it by some continuous function f of x, it will be just f of 0, because delta function at this point is multiplied by value of function f at the point 0. Yes? So if you consider, say, delta function on the sphere, yes, and consider integral delta of module x minus t f of x dx, integral over R3, for example, it is nothing but integral over sphere, center is 0 and radius t, f of x dsx. So integral over the sphere of the function. dsx is element of area on the sphere. Yes? And here it is multiplied by 1 over module x. Yes, so what is module x? Module x is just t. So, again, integral k of xt f of x dx over R3. Yes? kxt is 1 over x. Equals 1 over module x, but on the sphere module x equal t. 1 over t, integral over sphere of radius t, f of x dsx. Yeah, so we integrate it over sphere. But to be more simpler, I introduce here some coefficient. K of xt equals some coefficient, coefficient c, and here also this coefficient c, and this coefficient c equals 1 over 4 pi. 1 over 4 pi, it is it will be very convenient in a few minutes, you will see. So we can multiply by any constant, multiply by this constant. So how else can you explain it? So again, k of xt equals 1 over 4 pi t delta of module x minus t. We can consider some delta-like function. For example, we can consider k epsilon of xt equals 1 over 4 pi. No, to be accurate, okay, module x phi epsilon of module x minus t. So instead of a sharp delta, we consider its approximation. Yes, it is also solution of the wave equation, and this but this is a true solution without any reservations, because it is a smooth function and it is solution. But this sharp solution k is, I would say, more important for us, this limit. Now, how does it look in the space xt? Imagine that this is t-axis, and this is, say, x1, okay, this is x2, and this is x3. Yes, in fact, here in the base you have three-dimensional space, and all in all it's four-dimensional picture. Instead of this, let us imagine that the base is plane, yes, and this is another t-axis. I will draw as if it were two-dimensional, but in fact it is three-dimensional. So for any t, we'll have the plane, t is this, t is constant, and in this plane, this function will be 0, k xt, will be 0 everywhere but on the sphere of radius t. Yes, so we have here this sphere. Yes, so this radius of sphere is equal to t. So this means that, I'm sorry, let it be like this. This means that outside of this surface of the cone is module x equal t. Yes, so this is this cone, this surface. Outside of this cone, the function k is 0. And on this cone, it is a sort of density. It has some density on this cone. Now we'll see how it works. That's it. And now I go to the main point. Consider the initial value problem. Initial value problem for the wave equation. So first equation, u tt equals Laplacian with respect to x u. Yes. And we solve it in the domain x in R3, t more or equal than 0. So we solve it in this domain. And we have to give initial condition. We had this for the string equation. Now we have similar initial condition. U of xt for t equals 0 equals f of x. Ut of xt for t equals 0 equals g of x. So this is our full initial value problem in the three-dimensional space. Just imagine, I would say the function g of x is, say, continuous, and f is, say, c1. No, they are sufficiently regular so that the further calculations make sense. So we consider this initial value problem. Moreover, I want to consider the more restricted problem. Namely, I want to consider the problem utt minus delta u with respect to x equals 0. U for t equals 0 equals 0, and ut for t equals 0 equals g of x. So we consider this more particular, and further on we will reduce this general problem to this particular problem. And the claim solution u of xt equals integral k of x minus y t g of y dy y in R3. So k looks like a fundamental solution of this equation, or Green's function. No, here we have no boundary, so better to say fundamental solution. If you recall the solution of Laplace equation, Poisson equation in the whole space, then we had similar formula. Instead of this was k was Poisson, t was absent. So here we have different k, of course, one more variable, but it is still very similar. Okay, now how to prove it. Now let us substitute here the function k, u of xt equals integral of what? 1 over 4 pi t delta model x minus y model minus t. Yes, this is this k, g of y dy. Yeah. Now, what is this? This function delta model x minus y minus t is concentrated on the sphere model x minus y equal t. Yes? So it is 1 over 4 pi t. It does not depend, it can be, it's constant here. Integral over the sphere, sphere with center x and radius t. G of y dsy. Yeah. So again, we have here the point x. We draw a sphere with a center point x by following this formula, and we have to integrate the function g over this sphere, and then divide by 4 pi t, and this will be solution u of xt. Now, first of all, for any y, this is solution, yeah? Now we take different y, multiply by some coefficient, so this means that we take linear combination of solutions of the wave equation. So linear combination is also solution. Yeah, so first of all, this is solution, and then we want to study the properties of this solution to what, whether it satisfies the initial condition, these initial conditions. Now, to this end, let us look at this Let us look at this integral. Now, first of all, the function g is, I assume that it is continuous. Yes? This means that g of y equals g of x plus some small remainder when x is close to y. I'm sorry. Sorry. Gy gx plus, say, h of xy and h of xy goes to 0 as model x minus y goes to 0. Yes? So the first approximation will be if you replace gy by gx. So u xt equals 1 over 4 pi t integral over s x with radius t g of x plus h of xy ds x ds y. First of all, the first term equals 1 over 4 pi t times g of x times area of S of the sphere of S of xt plus integral h of xy dsy over s xt. And this first term equals area of a sphere in three-dimensional space equals 4 pi t square. 1 over 4 pi t times g of x times 4 pi t square plus something which goes to 0. One moment. If h goes to 0, plus all small of t. It's enough. All small, it is some variable which goes to 0 faster than t. So it's all small of t. Equals 4 pi cancels, g of x times t plus all small of 1. All small of t. Yes, so we have this is the main term. So what happens when t equals 0? U of x 0, let me write better, u of xt goes to 0 when t goes to 0. No, because this goes to 0 and this goes to 0 even faster. So this goes to 0, so the first boundary condition is satisfied. Now du dt, so u of xt divided by t equals g of x plus O small of t divided by t equal O small of 1, something which goes to 0. So this means that derivative of g, gt for t equals 0 equals ut. Ut for t equals 0 equals g of x. So the second initial condition is also satisfied. So this means that we found solution. So again, solution is has the following form. U of xt equals 1 of 4 pi t integral over x minus y equal t g of y dsy. Very simple solution. Very simple solution and very good. Now, what about complete solution? Solution of complete initial value problem. You see, we have already some experience in these things, starting from the string equation, so I can go without too much stopping. So now consider the following thing. What happens if you take derivative of this solution, time derivative, du dt? First of all, if a function satisfies this equation, the wave equation, and you take its derivative will also satisfy. Yes, let us call it for now v of xt. So v tt minus Laplacian over xv equals v is ut u t tt minus Laplacian x v t x u t equals derivatives, let me write u t t minus we have derivatives with respect to x and derivatives with respect to t. They are commutative. Yes, and so it means minus delta u t equals u tt minus delta x u t. Now, if u was solution of this equation, so here is 0, then time derivative of this 0 is 0. So it is 0. So the function du dt is solution. Now what can be said of this function utt? V equals du dt. V for t equals 0 equals ut for t equals 0 equals g of x, simply so. Yes? Now Vt, t equals 0. V is du dt, so dv dt is utt for t equals 0. But utt equals Laplacian u. Equals Laplacian u Laplacian over x u of xt for t equals 0. But u for t equals 0 is 0. Yes? So its Laplacian is also 0. And so this is 0. So this means that v, which is derivative of u, satisfies the following conditions. First, vtt minus v, Laplacian v, equals 0. V for t equals 0 equals g. Vt for t equals 0 equals 0. Yes? So just look, we have an interesting shift here. The function u satisfies these initial conditions. U is 0, ut is g. The function du dt satisfies this condition. It is g for t equals 0 and its time derivative is 0. So if, let me now replace g by f. Yes, by some other function f. So we first solve the equation, solve the initial value problem, vtt minus Laplacian x v equals 0, v for t equals 0 equals 0, vt for t equals 0 equals f of x. It's the first thing. Now we write w equals dv dt. It is the second part. And the third part is w satisfies the following equation. W tt minus Laplacian w equals 0. W for t equals 0 equals f. W t for t equals 0 equals 0. Yes? So we have this problem. And now what happens if you take the sum? We have u, v, w, which letter remains z of xt equals u of xt plus w of xt. So z tt minus Laplacian z equals 0, because it is sum of two solutions and equation is linear. Z for t equals 0, u is 0 and w is f, equals f. dt for t equals 0. ut is g, wt is 0. So it is g. Voila! We have solution of general initial value problem for the wave equation. You see how simple it is. So let me now write the full solution. U of xt equals solution of this problem, 1 over 4 pi t integral x minus y equal t, g of y dsy plus d dt of 1 over 4 pi t integral module x minus y equal t f of y dsy. So this is a full explicit solution. This formula is called Kirchhoff's formula. So this is a great formula, and we next time we consider different consequences of this formula and go further. For now, let's finish. Have a good time. Bye.